Welcome to today's lesson. We are on Unit 5 Vectors, Lesson 2, Operations of Geometric Vectors. First, let's take a look at addition and subtraction of vectors. Consider two students moving a cart in a classroom. They both push the cart, one with the force of 100 newtons and the other with the force of 120 newtons in the same direction. If we were using this diagram as our model, well, common sense tells us that the cart would move to the right with a total of 220 newtons. If one student then pushes the cart and the other pulls the cart in the same direction using the same forces as the above diagram, what would happen to the magnitude and direction of the total force? Well, again, we can conclude that the cart would move in the direction of the right with a total of 220 newtons. If the students decided to both pull the cart with the same forces as the above diagram, we would get the same effect. Are you starting to see a pattern here? That we can actually move vectors around? What about this final diagram? Can we use the same conclusion as the previous diagrams? Not so easy, is it? Which leads us into today's lesson. So when adding two vectors, you can find the equivalent single vector, and we refer to this as the resultant vector. Well, how do we find the resultant vector? Let's consider two generic vectors, A and B, as seen in this diagram. In order to add the vectors together, we must put them in an orientation that we call tip to tail, which means that the tip of A touches the tail of B. We can then draw and measure the resultant vector from the tail of A to the head of B. So basically where we start to where we ended. Again, this new vector is called the resultant, which is the sum of A and B. Another method that we can use is called the tail-to-tail method. If we consider the two generic vectors, again, A and B, we would just place them in an orientation called tail-to-tail. Parallel plus B is equal to A plus B. So by just drawing a diagonal across the parallelogram, A plus B then is our resultant. We can use either of these two methods in order to add vectors that are not parallel to each other or do not lie in the same line. It's important to know both of these methods because depending on the type of question we encounter, it may be useful to use one over the other. Let's consider the case where we have two vectors that are parallel or have the same direction. So for instance, if we have a vector A and a vector B, notice that they are parallel or they are in the same direction. What we can simply do is we can move vector B or vector A such that they can lie on the same line. The resultant is the vector from the tail of the first vector A to the tip of the second vector B. So when you add two opposite integers, of course the resultant is 0. So a similar result occurs when you add two opposite vectors. So let's consider a vector P. So I've got a little diagram here of the vector P and its opposite vector negative P. They have the same magnitude, but then just opposite directions. If we were to add them together, we would get the 0 vector. So this is a property of vectors. Let's consider this example. In orienteering race, you walk 100 meters due east, and then you walk 70 degrees east of north from 60 meters. How far are you from the starting position and at what bearing? Okay, so in these questions, the first thing I always do is draw a very nice detailed diagram. I often try and make it quite large so that I can sketch my angles and all my numbers in. Okay, so first thing is we want to, I draw a north. Okay, so there's our north. I use a fine pen. Okay, so I'm just going to read the question again. So in an orientation race, you walk 100 meters due east. Okay, so due east is directly east, and then walk 70 degrees east of north for 60 meters. I think I said from last time, for 60 meters. How far are you from the starting position and at what bearing? I always start off by drawing my compass bearings and then using different colors. If you have different markers, or you can go ahead and use that. Okay, so let's just say we're going completely east. So I'm going to start, we could start here and go that way, but I think it'd be easier because east vector will be the easiest one to draw. Okay, so there's my east 100 meters. Okay, so directly east. And then we're going 70 degrees for 60 meters. And you want to try and make your vectors to scale. It'll just help you visualize. Okay, so that's not quite 70, but I'm sure your diagram will be a little better than mine, hopefully. 60 meters, okay. And then we want to sketch. Okay, so already, okay, the first thing I always check is it tip to tail? So it is. So tip. So there's my first vector, and then I'm moving this way. Okay. So remember, vectors you can move around. So you could move this one over here and do a tail to tail if you'd like. Just remember that just to make it easier on yourself. Okay. So you can move vectors around. Don't forget about that. But you just want to make it the easiest diagram. So I'm going to leave it as such. Okay. So I'm going to draw a resultant vector from where I started to where I end, like so. Okay, so there's my resultant vector. Label that as R. And now what I want to do is use basic geometry and trigonometry in order to answer this question. So what we can say is we want to find the magnitude of this. Okay, I try and label everything that I can. So what I have here, this, you know that this is 90. Okay, so this entire angle then is 160 degrees. Okay. So what we can do is use, okay, remember, you can only use SOHCAHTOA when you have a right angle triangle. In this case, this is not 90 degrees, okay, and we're not given any other angle. So we have to use our other rules, sine and cosine law. So in this case, I have two lengths, a side, so two lengths, one unknown length, and an angle that's opposite to my unknown. Well, to me, I immediately would say I need to use my cosine law. So cosine law, and I would probably advise you to put this maybe over here. Right now, I know I'm not going to use this space, but just in case you do need to draw in other angles or whatnot, then you're not invading in your space here. So cosine law, we can say is a squared, generically is b squared plus c squared minus 2bc cosine of angle A. Remember that this angle and this side are opposite to each other. Small letters are the angles. Okay. So A, which is actually our resultant, squared, is equal to, I'm going to go ahead and actually fill this in, squared plus 60 squared minus 2, 100, it's 100, 60, and cosine of 160 degrees. Okay, and that just goes right into your calculator. So once I put that into the calculator, this is what I get for r squared, okay, and that's a vector. So taking the square root of that, the vector r then is approximately 157.7, okay? And we said that is in meters. Okay, so what that gives us is actually the magnitude, okay? So I'm just gonna go ahead and do this too. So just a correction. I also want to make sure that you acknowledge that that is a magnitude of r. We need to find the direction of r in order to complete this question, because it is a vector. So right now we only have the magnitude. What we need to do now is to find one of these angles so that we can define where its direction is. Okay, so in this case, what I would probably do is find this angle here. Okay, I'm going to find that angle. I'm going to use the sine law because I find that one the easiest. So using the sine law, okay, remember the sine law is, we're looking for angles, so I always put that on the top. Sine of A over the side of A is equal to the sine of B over, that's an A, and B. So remember that the angles and the sides are opposite to each other. Okay, so we want to find the sine, we'll say theta, over, and the opposite to that, okay, you can even draw an arrow, is 60, is equal to the sine. The only other angle I know is this big one, so we're going to say the sine of 160, and opposite to that is the number that we just found, 157.7. So then sine theta is then equal to, 0.130, and then theta is then equal to 7.5. And that, of course, is in degrees. Okay, so that gives us that angle. That angle there is 7.5 degrees. Okay, but that only tells us the angle. That doesn't actually tell us from what bearing. Okay, so if I said to you 7.5 degrees, would you know where to go? No, I need to be more specific. I could say that it's 7.5 degrees relative to east. However, let's use one of our more common bearings. Let's use quadrant bearing. Remember that I can move vectors around. So if I was to redraw this and I moved my vector, my resultant vector, okay, I said this was north, south, west, and east. And I redrew this vector, so it was over here, right? This was 7 degrees. Okay, if I just drew it over here, I moved it. All I did was move it. I didn't change anything else. I didn't change its size, its orientation. Okay, so I just said this was 7.5 degrees. This entire angle here is 90 degrees. So if I said 90 degrees minus 7.5 degrees, we have 82.5 degrees. So just leaving this separately, we're going to say that it is north 82.5 degrees east, okay, for quadrant bearing. So therefore, our final answer, and my pen has just run out, therefore, we have traveled 157.7 meters, 82.5 degrees east of north. And that would be a final answer.